Okay, so this video is for Cambridge International 9618 A-level computer science students doing their paper 3 exam next Friday. This is binary tree according to Cambridge International. So what is a binary tree? We've got nodes, and then each node can store up to 2 children. So some nodes might just have one child. Some nodes might have no children. So if a node doesn't have children, it's known as a leaf, and then the node at the top of the tree is called the root. The way that Cambridge International want you to implement this is using pointers. So basically from an array where the pointers are integers referencing certain positions in the array. So let's talk about the code for this. So we're going to focus on like a procedural implementation, as that is what is commonly kind of modeled in the past papers. So the procedures are going to affect the global state of the program. Obviously, what's more sensible is an object-oriented implementation. So at the end of the video, we might talk about that a little bit as well. So first of all, we want to say when we first load the program, we need to define some of our global variables, their initial states at least. So one thing is the tree, and the tree is going to be an array. So we're just going to define that as an empty list for now. And the free pointer is going to point to the next available node to be used in the array, and the root pointer is going to point to the top of the tree. In order to represent the node, we need to write a user-defined type, or a record, I guess. And because it's a record, we're just going to use public properties for the purpose of just having direct access from within the tree. Let's store strings, and the properties are data, which stores the string, and the left pointer, which points to the left child, or at least points to the index of the left child in the array, and right, well, self-explanatory. So let's write a procedure called initialize tree. Because we're using the procedural paradigm, we're going to make the tree global. In Python specifically, the tree is a list, so it's mutable, so we don't actually have to declare it as global. But again, let's try to match what we see in the mark schemes. And now we're going to define the tree as some empty nodes. Let's make a constant here maybe as well. So let's just have a global constant defined at the top of the program, and let's say the size of the tree is 10. Let's make 10 nodes, and we're going to loop through every node apart from the last one. And what we need to do is say, okay, that current node, we want to link it on the left. We want to link it on the left to the next node, I plus 1. So the reason for this is the starting state of the tree is not actually a tree, it's a linked list where every node should be, please forgive my crude MS Paint drawings. Every node on the left is linked to the next node, and then the right pointer is just unconnected. This is the kind of default state of the tree before we start breaking nodes away from the list and adding them to the actual tree, which we'll see in the next procedure. So we want to do that, and because we didn't include the last node, this means the last node remains linked to none on the left, which represents the last node that's available, basically. What else do we want to do? Now that we've created the tree, we want to say that the free pointer is the first node. So the next thing is we want to implement some sort of like add method, so add to tree, and we've got some new data. And these are going to be the steps. We first of all need to look at the free pointer to find the new node, and then we need to add the new data. Let's say the data was B. And then what we want to do is make sure that we acknowledge what it was linked to, so that next time we know what the next free node is. And then once we've remembered that, we can then delete this link. And then the whole idea is that we then need to link this into the correct position of the tree. So we're going to do a binary search tree. So say there's already data on the tree, which is A, and I don't know, That wouldn't make sense. Sorry, let's not start with A. Let's start with M, and this might be P, and this might be Z, and this might be N, and this might be A. So what we need to do is we need to traverse the tree to find the correct position. So the way the algorithm works is starting from the root node, we want to say, is this value bigger than or smaller than this value? So because it's smaller than, we traverse to the left branch. Then we want to say, is this value bigger than or smaller than? And because it's bigger than, this time we traverse to the right branch. So now we've hit a null pointer, as in a pointer that links to none. And then what this means is we've found the position for the new node. So let's implement that. So the first thing we need to check is if the tree is full. And the tree is full when the free pointer is equal to none. This is because what we said before, each time we're updating the left pointer, and if we reach the end of the linked list and there are no loads left, and then the last node links to none. Do you remember what we did at the start? We didn't do anything with the last node because we only counted up to the maximum size -1. So this is the check for this. And yeah, we probably would like raise an exception here if we're programming in Python, but again, let's match what we see in the mark scheme. So let's just print an error. Print error, tree is full. And we just need to make sure that none of the rest of the code in this procedure can now execute. So if the tree is not full, the next thing we should probably do is find the next available pointer. So the new pointer is equal to the free pointer. And we want to say, okay, the tree at the new pointer should, we want to set the data item to this new data that we've got. And we want to then update the free pointer. So we want to say tree at new pointer. So whatever the previous node, the previous free node links to on the left is the next free node. That's what this statement means. And then what we want to do is we want to break away. Once we've remembered that, we break away the node from the tree. How do we do that? Well, now we're overwriting the old node, the new pointer, and we want to say the left is now none. Right is already none because that's what we initialized it to. We were basically now breaking it away from this like free list. Now that we've done that, we want to check whether this is the first node in the tree. So this time we're going to query the root pointer. Oops, let's just do our globals as well. We want to query the root pointer, and we want to say, okay, if the root pointer is none, then this means that this node is actually the first node in the tree. So all that we now need to do is update the root pointer to the new pointer. If it's not the first node in the tree, then we need to do the traversal algorithm. And the way I'm going to do this is modularize it into a separate function, I think, called find insertion point. So we're going to pass in new data to this function, and then that's going to tell us what's the pointer of the node we need to connect to, and what is the direction. Do we need to connect on the left, or do we need to connect on the right? So let's write that module now. So find insertion point, new data, and this is the algorithm for this. So we want to start at the root, and we want to say while the pointer is not none, so until we find the end of the branch, and then we want to check whether we want to go left or right. So let's make a variable. Current is tree at pointer dot data, something like that. We want to say if the current one is smaller than the new one, then we want to set the direction to right. And we want to update the pointer ready for next time. So the pointer now should be the tree at that pointer, go to the right to find its pointer linked on the right. And obviously the opposite for that, so let's just do an else clause. And we want to say with, on the other hand, if it's not less than, then we need to go left. Is that the right way around? If the current one is left and go less, then go right. If it's not less, then go left. Okay, that seems to make sense to me. However, what we want to do is we need to make sure that we're keeping track of the previous node, because if we end, we can't just return pointer, because in order for this algorithm to get to this stage, then this condition must be false, right? So that means pointer must be none. So we don't want to return none. We actually want to return the previous pointer. So each iteration of this loop, we want to keep track of the previous pointer. We probably should initialize this as well. So let's make previous pointer. Oh no, we shouldn't need to do that. Should we need to do that? Let's just take a copy of the current pointer. Then each iteration we want to move to the next pointer, but at the same time remembering where we came from, essentially. Hopefully that works. So what do we need to do next? We have the pointer, so we know where to connect it to. Now we just need to update the existing pointers to make the connection. So something like tree, we want a query direction. If direction is equal to left, then this means we need to update the tree at the pointer on the left and connect it to this new node that we've got, which is new pointer. Otherwise, we want to do the same thing, but on the right. Okay, I'm not guaranteeing that this will be bug-free, but let's run in a second. Let's just write one more method, traverse the tree. Commonly what you'll be asked to do is traverse the tree so the data items are printed in alphabetical order. So let's do this. So we want to say if the pointer is none, it's going to be a recursive algorithm. If the pointer is none, then set the root pointer to, set the pointer to the root pointer. Because, so basically what we're going to do is we're going to add some items and then we're going to call traverse tree. But because it's a recursive algorithm, we don't need to pass in the argument the first time because it's always going to be root pointer. I guess we could pass in root pointer here as well. And then what we want to check is, let's say left, and left is this, the pointer on the left. To make an alias to make it easier to type. Right is tree pointer dot right. And when we're traversing, we basically want to say, if there's something on the left, go left. If there's something on the left, no, there's not. So we need to go back. Then we want to print our item, A, that gives us the first data item if we're going in alphabetical order. And then we want to say, go right. And then we want to say, go left, can't go left. So print. So we've got A, B, go right, can't go right. So then we go back. And then we finish this node. So we go back. And then we've done left. So then we print M. So A, B, M. That's in order. And then we've already gone left. We've already printed. So we want to go right. So the order is basically left, print, right. So what we want to say is if there is something on the left, if left is not none, then we want to go left. And the way we're going to do that is we're going to recurse. We're going to make this recursive procedure call itself and pass in the left pointer. Do it again for the node on the left. Then we can print the item, the data, sorry. Let's say print data. We might as well make another alias here. Pointer.data just makes it a bit easier to write. And then we want to do the same thing with the right. If right is not none, then basically visit the right. Okay, should be time now to set up some test data. So let's make another module called test. And in test, what do we want to do? Let's define our globals, just so it updates program scope. And let's initialize the tree. And let's loop through some data. So for animal in mouse, cat, dog, horse, sheep, goat, bat, lizard, lion, tiger, cheetah, giraffe. Something like that. Just some animals. Let's do a multi-line string and just split them. And then what we're going to say is add to tree with each animal. And so what we'd expect here is we'd reach the maximum capacity, and then some of the items should generate this error message, right? So after we've added to the tree, let's traverse the tree, and then what we should expect is if the binary tree has worked properly, we should see these animals printed in alphabetical order. So bat should come out first, despite the fact that mouse will be the root pointer. We should have bat, cat, dog. Missed out cheetah. Bat, cat, cheetah, dog, etc. So we should see the animal names printed out in alphabetical order. Let's call this binary tree, something like that. All right, let's run the program and then debug. So we've got an issue in that the pointer in the traverse tree operation is giving us a non-type. So why is that happening? Because pointer should never have been non. I'm guessing there's some sort of problem. We didn't manage to print any nodes. So I'm guessing there's some problem with the root pointer not being updated. So we've got the root pointer. The root pointer is non. So we should be having the root pointer being the new pointer. The new pointer comes from the free pointer. The free pointer should have been 0. So to help us to debug with this, let's print some messages like added some f strings. Added new data to the tree. Add some messages. Root pointer was set. And we're getting some issues with, oh, sorry, because I'm calling traverse tree down here with an empty tree. Oh, so let's actually fix that. So let's put something in place. We probably want to put something like if root pointer is none, then let's just print a message, cannot traverse, tree is empty, something like that, and then let's just return. Sorry, my cat is making some noise in the background. So let's try that. So that stops that error from occurring. And now what we want to do is want to call the test procedure, right? So let's put that in the main method down here, test, the main program, I should say. So did it work as expected? So we iterated through this list of animal names. It added each node to the tree. Unfortunately, we couldn't fit cheetah on and we couldn't fit giraffe on because as we set the size of the tree to 10 at the start with this global constant, and then when we traversed the tree, bat, cat, dog, goat, horse, lion, lizard, mouse, sheep, tiger, we succeeded in printing the animals in alphabetical order. So just a reminder for your syllabus, there's no requirement to work out how to delete a node from a binary tree. You just have to know how to add something, traverse something. I guess search might be another question. So maybe let's just program that quickly. Search tree. So search a tree for some data. And then the algorithm would be to, again, start the root pointer and check while the tree at the data is not equal to, while the tree at the pointer is not equal to the data that we're searching for. And we probably should check that while pointer is not non, and something like that. And then we basically want to do the same thing that is in the find insertion point algorithm. We want to go left, and then let's just check the condition, like why did we exit the loop? If pointer is non, then print that must signify that the data was not found. Otherwise, if we have exited the loop and it's this condition that caused us to exit, then that must mean we found the position. So let's say data was found at position pointer. So yeah, maybe let's test that. Let's search the tree, search tree, search tree for mouse. Let's see if it works. Help if I name the parameter the same thing. But obviously it wouldn't make sense. It wouldn't really make sense to call it new data. Search tree mouse. Mouse was not found, so it's not working at the moment. So let's think why that's not working. So pointer. Ooh, okay. So we don't want to update this. So let's instead make this as a flag controlled loop. So search is true, and let's say while search. And instead let's invert these conditions. So we want to say if pointer is none, then that must mean we found the end. We can't find the item. So I guess we could just return at that point. Otherwise, we want to say if tree at pointer is the data, then we found. Again, I wouldn't normally do this. This is a procedure, but I'm adding the return keyword. Again, this is what's modeled in the pass mark scheme. So in order to kind of prematurely end the procedure, you can just do an empty return. So we found the data, let's print it, but then otherwise we want to check where to go next, don't we? Maybe I don't need to do the return. So let's see if that works, if converting it into a sort of flag-based loop instead. So if we do that, then search becomes false. If we do that, then search becomes false. Otherwise, search remains to be true. Let's try that again. Oh, that's not a valid expression. Maybe that was causing the problem. We wanted to take the data field from the node, not the node itself. Actually, seeing as I'm already making reference to that as current, let's just say if current is data. Try that again. So search tree for mouse. Mouse was found at position 0. That seems to make sense because mouse was the root node. Let's try something that was added later. So tiger, for example, should have been found at position 9. So that seems to work. I'm not really sure why you would do that because obviously the array indices, this is how the tree is actually represented in memory. Each is just a node, and then it's the pointers that change. So the values, the left and right values that change. Okay, that's almost the end. So let's just talk about what could differ. So obviously you could have a sort of like class-based implementation instead, where each of these would become methods, and instead of using global variables, they would be instance level properties. So self.something, probably best to use private properties, and maybe even the case of the node then would be contained within the tree. So that's one possible implementation. Something else we've seen is doing away with the concept of a node altogether. So instead of storing a node, then there'd be some sort of like two-dimensional data structure where there'd be a left pointer and a data value and a right pointer stored in every index of the tree array. So something like that is also possible. So because you're being assessed on the syllabus for understanding how abstract data types can be implemented from other types, then you need to be ready for those sort of variations that they might ask you. All right, thanks for watching.